Hi, my name is Hayden Smith, and this is part 3 of the Batlab video series. In our last video, we discussed the prerequisites for using the Batlab utility script that has been developed with the Batlab Python library available from our public GitHub repository page. In this video, we'll be going through the steps necessary to run a simple cycle test on a 18650 form factor cell using the utility script and your Batlab unit. Now, most of what I discuss here will actually be covered by this Batlab Python script quick start guide that was referenced in the preceding video and is available on our resources page on the Lexilon website, which I will link in the description of this video. However, I do feel that it is probably useful to have some commentary along with a more hands-on tutorial for those of you who prefer that type of learning environment. So, just to jump right into the guide before we proceed to the script. At the bottom of that documentation there's a section for the Python utility script usage example, and I want to speak to kind of a higher level approach of what we are actually going to be doing when we execute the Cycletest command. When you ever use your Batlab to test a batch of cells, the questions you ask yourself are, what are my safety thresholds and what are my test configurations for this particular batch of testing? You want all your cells to be tested in the exact same manner so their outputs will be comparable to one another. If a cell is tested with maybe different discharge or charge rates, then those results will no longer really be comparable. So the way we kind of standardize that from an architecture perspective is by use of test settings, or what we call test playlists. And these test settings are in the JSON file format. Within those JSON files, there's a list of all these parameters, and they each have an impact to your test setup. So there's a screen grab of a default JSON file that's included in the materials that are downloaded with the utility script, and it actually indicates each one of these JSON parameters and some values there. And I want to talk about those values because there's an important table beneath that screenshot. Each of the parameters is kind of defined in this table alongside the units of the parameter, as well as there are two columns on the far right that indicate the minimum and maximum value for that parameter. And that's really important to note here because the utility script does not currently gate you from setting these parameters to a value that's outside of these operational ranges. The future polished GUI will definitely have that constraint put into place, but we do advise you to please reference this table when you're creating your test settings files, because we do not want to operate outside of these operational range that we created in mind with hardware constraint in mind while developing this table. So if I take a look over here on the left, I've actually pulled up in Notepad++ a Batlab demo.json file that I'll be using for this exercise. This Batlab demo.json extends exactly from the example screenshot kind of over here on the right side with this documentation. I've just modified the numbers a little bit to fit my needs. So on the left side, I'm just going to go through each one of these and describe what they are. Acceptable impedance threshold. So as documented over here in the table, this is going to be a future feature wherein if your impedance measurement exceeds this threshold, you would just immediately take that cell and stop testing and essentially state, this is beyond the limit that I'm comfortable having in my project, so let's just stop testing right now and we'll put it over to the side for maybe a different project or for recycling. On the test. However, it does output to the measurement file as kind of a comment, because it's important to maybe be able to trace your measurement output to a specific version of the software in which that measurement output file was produced. The cell names, this is an array of string values that are comma separated and basically should line up with your physical labels on your cells, whatever kind of naming scheme you have. If you're going to test 4 cells in your batch, you want to have 4 entries here, and you want those names to line up exactly with what you've maybe labeled your cells physically with maybe a post-it note or whatever you're using there for your cell naming convention. The cell playlist name impacts the measurement output file name, and that measurement file will basically use this as kind of a prefix. So you maybe want to have it reference your project, maybe also reference something about the cells you're particularly testing if you got kind of a naming scheme there like I mentioned before. And then we move on to the parameters that have a functional impact on your test. The charge current safety cutoff. So in the charge phase of a test, what's the maximum current you're comfortable with? If you exceed that, you'll stop the test. So simple enough, I've set it to be 4 amps. The charge rate. So in the charge phase of a test, what current should I charge at? And I have it set to 1.5. Should be supported by my Explorer board here on the right of my chair. Charge temperature cutoff. In the charge phase, what's your temperature cutoff? And this is in units of degrees C, which is documented over in the table. I've got the charge temperature cutoff, degrees C. Okay, discharge current safety cutoff. So it's basically the flip now. So in the discharge phase, what's my current? And I'll just have that be the same as 4. Same for discharge rate, 1.5 amps. Discharge temperature cutoff, that's configured separately, and I've just got it set to 65 degrees C. High voltage cutoff, that's the voltage at which you will stop the charge phase of a test. So if I am charging at whatever current rate I have selected and I reach that 4.2 volts, I'm going to actually stop. And before I enter into the next phase, which would be the discharge phase. Impedance reporting period. So that's in the units of seconds, and that defines the space in which you allow to pass before you take impedance measurements. So in this case, we've got a 5-minute window in between impedance measurements. Low voltage cutoff, I've got it set to 2.8 volts. That is good for my test here. So that's analogous with the high voltage cutoff, but it's for the low end, so in the discharge phase. Now we get to measurement cycles. So we see we've got reporting period, warm-up cycles, and measurement cycles. Measurement cycles are the number of cycles that are actually going to take measurements, but you can actually precede measurement cycles with a specified number of warm-up cycles. So if you'd bought new cells and were trying to break them in before you actually did measurements, you could apply a certain number of measurement cycles before you enter your actual measurement cycles and actually get those recorded data. The reporting period is and that's in units of seconds, is the time in which is the space between measurements, so that's just 1 second. Rest period, that's the period of time in between completing a phase of a test, so maybe the charge to discharge phase, the discharge to charge phase, at which you allow the cell to rest without any charging or discharging before you enter into the next phase. Sine wave frequency, that's the frequency of my impedance waveform, which is right now in 39.0625 Hertz. It's very important on this one, only set this to be integer multiples of this 39.0625. So the next step, I'd multiply this by 2, I could multiply it by 3, etc. Anything that's an integer, and it has a maximum value, which is defined over here on in our table. The sine wave magnitude, that's a little different here. So it's a discrete selection from 0 to 3. So you can do 0, 1, 2, or 3, and it corresponds to different amp peak-to-peak values. So over here on the right side, our table defines that a value of 0 here actually is a 2 amp peak-to-peak impedance waveform. Storage discharge. So this is a Boolean indicator. If you want to discharge your cells to a known voltage state at the very end of your cycle test, you can set this to true and then specify a storage discharge voltage. So in this case, I've got 3.7 volts. So at the end of all my testing, all my cells should be at the 3.7 volt level, which is great. Good storage, everything's in a known state. So with all this in mind, I've got all my parameters defined in this Batlab demo.json file. And if I were to look over here in my Batlab directory where my Batlab util.py script is, my JSON file is in the same directory there. So that'll be important here in this next step. So I'm going to go ahead and pull up my command window, and I'm going to navigate to my Batlab folder. So I just got to cd into that folder. If I type dir, I'm going to confirm that I'm in this JSON file with my Batlab util.py script. And if everything's set up properly from my preceding video, I should just be able to type Batlab util to execute the script. The first output we see here on the left side is a list of all of the commands that are available to me within the command line interface. It's got also their syntax, and then on the right side we have a description of what that command does. So at this point in time, I actually have one Batlab unit connected to my computer with the 5-volt power supply attached to the 5-volt header. So if I press the enter key, I'm actually going to get the script to detect my Batlab unit being connected and set to the active Batlab that will receive my commands. I see that it has been assigned a communications port of COM3, and that is great. So in the test command list, I'm going to see I have a Cycletest command, and then I've got a discharge test, a load settings, and view settings command. So for the purpose of this exercise, I'm going to streamline this just by going through the essential commands we need. The first thing we need to do is load our test settings. So if I type in load settings, and then I give it my Batlab demo.json, I'll press enter. So that reads from the directory that I'm in, and it tells me that it is basically going to output my measurement file to a batlab-log _ solar car project. So if you recall, on our notepad file, solar car project was our cell playlist name. So that played a role here in our measurement file. And then it reads back all the parameters I've just loaded, just for a sanity check essentially. And so everything checks out. And now the next command I run will be to execute a test on a cell. So I've populated a cell into the cell 0 slot of my Batlab unit, and if I now type the Cycletest command, I can type Cycletest, give it my Batlab cell slot name. So if I do Batlab cells 0, and then give it my cell name. So in cell name, in this case, we're referring to the cell name parameter of this file. So I'm going to pretend as though I had labeled this cell solarcar-001. So I'm going to call it solarcar-001, and then I press enter. So at this point in time, my Batlab has kicked on and has started the test. One of the commands we have available to us is the measure command. So if I type measure, I'm going to get a reading of all my cell channels with a reading of their current voltage, the amps, the current charge rate, the temperature, and then the number of units of charge placed onto them during a test, and then the mode the cell channel is in, and then whether or not there has been any error. There have been any errors. So the measure command is one of the essential commands to using this utility script. Instead of just typing measure, I can actually provide a specific cell channel that I want to measure, and it'll actually just provide back that one. The other cell slots we see here have a reading of about 1.6 volts, which is actually expected because that is about the floating voltage we expect when there is no cell populated into the channel. The coulombs reading here, you'll note that on cell 3 we have some charge left over. I was messing with this cell 3 slot earlier with the cell, and this cell channel or coulombs register actually has to be reset independently. So that's the reason that we had a little leftover value there. I had not yet reset it. So I'm going to let this cell run for a little while so that I can demo the output measurement file. But essentially what's going to occur is our cell will eventually reach the 4.2 volt cutoff. It will enter the stopped phase for a period of time that we specified as 60 seconds, and then it will enter into the discharge phase. Once it reaches our 2.8 volt cutoff on the lower end, it will stop, wait 60 seconds, charge back up to the full amount, and then we've reached our full charge cycle. We've gotten to from our full limit to the lower limit, and then back up to our high limit again. And at that point, we'll enter the final storage discharge phase. It will discharge down to 3.7 volts, and the test would be officially complete because I set it to just have one measurement cycle. So I've let this run, and I'm not going to do the whole test here. It would take obviously a greater period of time to show the whole results. But I'm going to stop the test. So if you want to stop a test ever, you can actually use the stop command. Stop cell 0. If I measure cell 0 now, I'll see that I'm in the stopped mode. And then I'm actually going to go ahead and reset cell 0, which places it back into the idle state. That is the state at which I have a cell populated in the channel, but I'm not running any test, and it's in the correct polarity. So if I pulled up my folder here on the right now, I'm going to actually take a peek at my solar car project CSV. So I've got this open with Notepad++ again. The first thing you'll see at the very top is a comment with the measurements settings that were used to create this measurement file. So it's got everything we just did, which is great, because now you know if you had separate measurement files and wanted to know if your results were comparable, you could do a quick test between these notes to see, okay, where they tested the exact same way. Then at the bottom we get the CSV headings here for our different columns. So we've got their cell name, Batlab serial number, a timestamp, or the channel that the measurement was taken on, the timestamp and seconds that the measurement was taken, our voltage reading, current reading, temperature, impedance, and then we've got placeholders for all these other potential readings here that we can configure, and we don't have those placed in there at this point in time, but that is just showing the potential of what we could be able to place in these empty enumerations here later with different firmware and different software, and when we have the GUI ready to go. So with this setup, we have essentially measured over a couple minutes here several measurements on the cell, and we have current readings, temperature readings, so you can imagine that over however long this test would have taken, we'd get a lot of readings that can be used to generate a lot of great graphs, a lot of great comparable results, and take that data and actually manipulate it and do analysis on it to determine characteristics about our cells. So with all this being said, there'll be a future video to go through the more involved commands that we saw here in our script. We didn't touch on all of them, but this did kind of go through the essentials of what we saw in the test or the quick start guide, and I hope you'll stay tuned for the next video and that this video was helpful. And of course, if there's any questions that you have, if anything didn't make sense and needs to be additional input on, feel free to let us know. Thanks for watching.